The ABC of stellar evolution, a look at the birth and the life and the death of stars. So when we look out into the universe, we see, of course, billions, if not trillions of galaxies, each of which have got maybe hundreds of billions of stars in them. So the question I'm trying to address this evening is, how do these stars work? So we'll be looking at birth and life and death. Birth, how do stars ignite in the first place? Where do they come from? How do we get nuclear ignition? And then looking at the life of stars, how all stars are a question of the balance between radiation and gravity, and looking at the lifetime of stars, low mass and high mass. And then asking the question, what happens when stars come to the end of their lives? And in star death, we'll ask ourselves, do they end their lives with a bang or a whimper? And what is left afterwards? Possibly a white dwarf, possibly a neutron star, possibly a black hole. Let's just remind ourselves of the rough life cycle of the sun in terms of billions of years. On the left-hand side there's the Big Bang. I gave you a talk some time ago about the beginning of everything, how the Big Bang was the origin of all of the hydrogen in the universe, and some of that hydrogen, after a few billion years, collected together to make our sun. So we are currently there at 13.8 billion years after the Big Bang, and our sun formed something like 9 billion years after the Big Bang, and so the sun is about 5 billion years old. So in other words, it's pretty much middle-aged because it's going to last another 4 or 5 or perhaps a little more billion years into the future. But once the fuel does start to run out, the sun is going to expand into a red giant, and after it's gone through its red giant phase, what will be left is a very small white dwarf. Bear in mind, none of this cartoon is supposed to be to scale. It's just a reminder of, roughly speaking, what it is we're talking about. A middle-aged sun in the middle of its life, in the middle of its stable life, but after a few billion years, it's going to change dramatically. And we'll have a look at this in a little more detail as the next few slides unfold. So what's going on at the heart of a star? In the core of a star, where the pressure and temperature are high enough, we will get fusion of hydrogen into helium. In other words, protons, which are positively charged and don't want to get very close to each other, if the temperature and the pressure is high enough, we can force these positively charged particles together and fuse to make heavier and heavier elements. And in the center of our sun, we are effectively fusing protons, 4 hydrogen nuclei, shown schematically in this cartoon as 4 individual protons. They are being fused together to make one nucleus of helium, shown as 2 protons and 2 neutrons. We're not going to worry about all of the nuclear physics that goes on in that little white flash in the middle there. That's important to a nuclear physicist, but as far as we're concerned, all that matters is 4 hydrogens go in, 1 helium comes out. And every second, 620 million tons of hydrogen is converted into 616 million tons of helium. A slight deficit there, a little less than 1% of the mass of the sun is being converted from matter into energy, and that energy is of course responsible for lighting up and keeping warm the rest of the solar system. So stars are not just nature's way of lighting up the universe, they are fusion factories because they can fuse hydrogen into helium, and ultimately, as we'll see shortly, they can fuse helium into ever more heavy elements. So you could say, well, that's fine, start with hydrogen, make helium, use helium to make carbon and nitrogen and oxygen and all the other elements. But you could stop at this point and say, yes, but where does all the hydrogen come from in the first place? But I defer that to the previous talk I've given you. It's a very good question, of course, where did the hydrogen come from? But that's a different talk, and I'm going to assume in this talk that we simply live in a universe that's almost full of hydrogen, and we're asking, how do we use that hydrogen to make stars? So where do stars come from? You might think it's a rather tricky business to make a star, but actually it's a lot simpler than you think. Anyone can make a star. It's really easy. All you have to do is to follow these 5 really simple steps. Start with a big cloud of hydrogen. Wait some more. Wait a bit longer. Okay, you now have a star. That's pretty much it. If you start with enough hydrogen and then just let gravity do its stuff, if you are patient enough, you will end up with a star. We're familiar with the idea of the galaxy being full of nebulae, such as this beautiful nebulae, the M42, the Great Nebula in Orion. These are effectively stellar nurseries. They are generally pink simply because hydrogen tends to glow pink when it's excited. It has a number of different optical lines, a number of different emissions of light, but it's dominated at the red end of the spectrum, and so you tend to get these sorts of colours. So whenever you see a large cloud of gas anywhere in the galaxy that seems to be pink, you've probably got a lot of hydrogen there. So what is it that triggers star formation? Well, the galaxy, and we assume not only the Milky Way, but essentially all galaxies, seem to have giant molecular clouds floating around them. So what is a giant molecular cloud and why are they called that? Well, they're called that for 3 very good reasons. 1, they look like clouds. 2, they consist mainly of hydrogen molecules. And you can probably guess where I'm going with this. The 3rd reason they're called giant molecular clouds is because they're big. Typically, giant molecular clouds can be not just a few light years, but generally dozens, if not hundreds of light years in size. And these are very common. We can see lots of them floating around the Milky Way. So what is it that makes a giant cloud of hydrogen collapse to form stars? Well, there are a number of possible trigger mechanisms. For instance, given that all of these clouds are rotating like everything else around the centre of the Milky Way, ultimately they're not all in exactly the same orbits, and therefore sooner or later one cloud will collide with another. And when 2 clouds collide, it can trigger the collapse of one or both clouds. It's also possible that a GMC, a giant molecular cloud, might collapse because of a shock wave that ripples through the cloud. Where could that shock wave come from? Well, one shock wave might be the death of a previous star. If a star dies and goes supernova, it can produce shock waves that go some distance away from the star and can propagate many dozens, if not hundreds of light years through other molecular clouds in the galaxy. So the death of one star might trigger the birth of new stars. It is also possible for a cloud to collapse being triggered by galaxy collisions. And although galaxy collisions sound quite cataclysmic, when I described the ABC of galaxy evolution, I tried to make it clear that collisions of galaxies are by no means odd events. They are perfectly normal parts of galaxy evolution. Galaxies grow by merging with other galaxies, and so one galaxy colliding with another is a perfectly natural part of galaxy evolution and not quite as cataclysmic as it sounds. So when we look at a galaxy like this, we see, perhaps I hope it's clear, that the colours of this galaxy, you see little dots of pink around, especially in the spiral arms of the galaxy. There's lots of little dots of pink. These are the giant molecular clouds that I mentioned earlier. And it's the collapse of these clouds of hydrogen that ultimately will produce new stars. And when we see galaxies interacting with each other, here Messier 51, the Whirlpool galaxy, this satellite galaxy on the right is disrupting the spiral arms and it is producing yet more pink. In other words, there's more star-forming regions because of the tidal interactions, the gravitational tug of this satellite galaxy. It's producing more and more star formation. The more disruption we get to a galaxy, it's common to find the more pink regions we find. In this particular case, the antenna galaxy, seen in a rather wide field, so you can see the actual antenna that give it its name. But if we look in more detail with the Hubble Space Telescope at what's going on in the galaxies themselves, Again, we see very dense regions that are flooded with pink, indicating the collision of these two galaxies is producing a whole load of new star formation. What's going on locally with the Milky Way? Well, we think there have been interactions with other galaxies in the past, thanks to the Gaia spacecraft. That's told us that we have been interacting with galaxies, and it looks like we will be interacting with the Andromeda galaxy in the not too distant future. In a few billion years, the Milky Way, shown in the top right, and the Andromeda galaxy, shown in the bottom left, are probably going to collide with each other. In this particular simulation, the Triangulum galaxy in the top left is merely a spectator. Sooner or later, that is going to collide with us as well. But when galaxies collide, very few stars will actually hit each other because the stars are separated by such vast distances. But the gravitational tug of one galaxy on another will disrupt the spiral arms of both, and the gas will interact, and the gas clouds of one galaxy will trigger star formation in the other. So when these two galaxies do merge with each other, you can see the time scale in the bottom right hand corner there, many billions of years into the future, there'll almost certainly be new star formation in this process. Here we see what it might look like from the perspective of Earth. Bear in mind, because stars don't collide with each other, there's no reason to think that the solar system won't survive the collision of the two galaxies. So if the Earth is still around at this point, this is what it might look like from our perspective. There's the Andromeda galaxy in our sky, and of course the Milky Way is a large band of light because we are sitting inside the spiral arms of our galaxy. As Andromeda gets closer and closer to us, it'll be an absolutely spectacular sight as it approaches us. You won't need a telephoto lens to get a nice image of the Andromeda galaxy. You'll need a wide-angle lens to get it all in. And as the Andromeda galaxy passes through our galaxy, as I've mentioned earlier, any of the gas that's around in either galaxy will be triggered to collapse and make new stars. And there will be a riot of new star formation, as shown by the pink regions in this simulated image. It'll be so busy at this point, some 4 billion years into the future, that it'll be essentially impossible to tell which star used to be part of Andromeda and which star used to be part of the Milky Way. And almost certainly the star formation rates will go up enormously when this happens. So if we take a smaller view and ask what happens if we just take one molecular cloud of hydrogen and ask what does it look like when that cloud collapses to make a star. So here we're starting, it might look like we're starting with a star, but no, this is simply starting with a computer simulation of a large spherical cloud of hydrogen. You may think that's a little unrealistic to start with a cloud that's spherical rather than one that is rather ill-defined and ragged. Well, yes, that's true, but it's simply easier to start the simulation this way. So there's a whole load of hydrogen in this cloud, and the computer simulation starts with every little bit of the cloud being given a slightly different temperature, a slightly different pressure, with the individual molecules of hydrogen moving in a random direction. And then we can say, right, let gravity do its stuff and simply see how this cloud evolves. So let's run the simulation. So here we go. Some parts of the cloud seem to be moving out, but most of the cloud is collapsing towards the center. And as it gets denser and hotter, the colors are changing in this simulation from orangey to yellow. We can zoom in a little bit to see a little bit more. But the pressures and temperatures are getting high enough in some parts of this cloud where fusion is taking place. Remember, we have to overcome the repulsion of protons before they can fuse together. But if the temperature is high enough and the pressure is high enough, we can fuse hydrogen into helium and a star is born. So each of these white dots represents the birth of a star. And you can see that after a while, it turns into a popcorn machine. It's not simply a question of this cloud generating 1 or 2 or 3 stars. If we start with a cloud that's 100 light years in diameter, we can generate hundreds or possibly thousands of stars, ultimately in a star cluster. you notice that some of them stay fairly close to where they were born, some of them get ejected and move away from the cluster. If we zoom out and rotate, you can see that the cloud is a rather different shape now. The outer parts of the cloud are very dark as most of the hydrogen has been used up, but there's still a fair bit of hydrogen left, even after making thousands of stars. And we think our sun was born this way. Our sun was probably born with perhaps 3,000 siblings in a cluster like this, but it just so happens that the sun was born with enough velocity that it left this particular cluster. And it's almost impossible 5 billion years later to figure out which particular cluster was our sun born in. But if we think this simulation is a good way of thinking about how clusters are born, we can take that result and ask ourselves, well, does that bear any resemblance to the sort of open clusters, the galactic clusters that we see in the galaxy? Does this look anything like an open cluster? And if we change from a simulation to an actual observation, well, yes, it does seem to bear some resemblance. Here we can't see the hydrogen that gave birth to this cluster, but it looks like the arrangement of stars that we get in three-dimensional space does bear a simulation, a reasonable semblance to what the simulation is telling us. We have to remember that every star, in terms of what's going on inside, every star is a question of balance. Because gravity, universal gravity, is always pulling the material of the star inwards. And we've said that if the pressures and temperatures are high enough in the centre of a star, then fusion will fuse together hydrogen into helium and it'll release energy, so there'll be radiation pouring out of the core of the star where it's hottest. Gravity pulling in, radiation pushing out. All stars are a balance between these opposing forces. Gravity pulling in, radiation pressure effectively pushing the star out. When these opposing forces are balanced, then the star is stable, effectively like our sun, middle-aged and well-behaved and in balance. If it ever gets out of balance, the star must evolve. And many aspects of how stars are born and how they live their lives and how they eventually end their lives can be explained in terms of that balance and what I like to think of as the A, B and C of star evolution. So what are the A, B and C? Well, the A stands for accelerated fusion, because if we want to generate fusion, we have to get positively charged particles like protons pushed together. They don't want to get particularly close because they're both positively charged and like charges repel. So we have to have the temperatures and the pressures high enough to get them close enough to fuse together to then release the nuclear energy. So we can get accelerated fusion if the temperature and the pressure are high enough. The B of the ABC, well, we've already seen that. That's the balance. A star is in equilibrium when gravity and radiation are in balance, and the star is happy when the two are balanced. And the third element of the ABC, C, stands for compression produces heat. We all know that simply because if we try and pump up a bicycle tyre, the pump and the air inside the tyre get hot, as well as us getting hot because we're doing a certain amount of work as well. But we know that compressing a gas heats it up, and the opposite is also true. If we allow a gas to expand, it cools down. So we can understand a lot about stars just thinking about those three concepts. Push particles together, we can accelerate fusion. Stars are a question of balance, and compression produces heat. We'll see how it works in detail when a star comes to the end of its life. And how long a star lives depends on its mass. This is just a reminder of how we classify stars. So the vertical scale is luminosity in units of the luminosity of the sun, and the horizontal scale is temperature, historically cold on the right, hot on the left. So there's our sun in the middle of the main sequence with a luminosity of 1 by definition and a surface temperature of a little shy of 6,000 Kelvin. Remember, this is simply the surface temperature. This is nothing to do with the core temperature at which nuclear fusion is actually taking place. So we can think about how long a star lives for. Stars of different mass follow quite different lives. If we think about a high mass star, many times more massive than the Sun, for instance, well, they've got a lot of fuel. So you might think a high mass star with much more fuel than the Sun might last longer. But actually, because the gravitational forces are so very strong in a high mass star, gravity is pulling on all of this mass, so you need to burn the fuel, you need to fuse the hydrogen into helium much more quickly in order to balance that strong force of gravity. To maintain balance, you need a lot of radiation to be generated. And that means the nuclear fuel actually must be used at a prodigious rate, a lot faster than you might expect. So although you're starting with more fuel, the fuel runs out faster. So rather than living for perhaps billions of years like our Sun, with a nominal lifetime of perhaps 10 billion years, a high mass star might only live for a few million years. And if we take the opposite end of the spectrum and ask what happens to a low mass star, again, it's not quite as intuitive as you would expect. You might expect if a star hasn't got much fuel, well, it's not going to last very long. But actually, low mass stars, because the gravitational forces are rather weak, you don't need particularly fast nuclear reactions in the core. You don't need strong radiation forces to balance that gravity. And hence the nuclear fuel, although there's not that much of it, can last an awful long time. For instance, a star that's only 10% the mass of the Sun, well, we're not actually sure what happens at the end of its life because it's not actually ever happened. For a star that's only 10% the mass of our Sun, we would expect its lifetime to be much longer than the history of the universe. So even a star that was born 13.8 or more billion, or less billion years ago, well, it won't have come to the end of its life yet. So we can work out with simulations and equations what we would expect to happen, but we've never seen a low mass star come to the end of its life. Let's just take a little bit of a diversion just for a bit of fun and ask, okay, mass makes a big difference to how stars evolve, but what about sizes? A star's mass might be 10 times or perhaps even up to 100 times as big as our Sun or smaller than our Sun. But that's mass. What about the physical size in terms of diameter? The diameter of a star can vary by much more than just 1 or 2 orders of magnitude relative to our Sun. If we think about diameters, let's just for a second remind ourselves about the sizes of planets in the solar system. So this is not in the conventional order of distance from the Sun. This is the planets in order of size: Mercury, Mars, Venus, Earth. Let's take Earth from the right-hand side of that panel and put it on the left-hand side of the next panel. So there's Earth in the bottom left. Then we've got Neptune and Uranus, the ice giants. Then we've got Saturn and Jupiter, the gas giants. So Jupiter, of course, something like 10 times the size, or something like 1,000 times the volume of Earth. So let's take Jupiter and put that in the bottom left, and now we're looking at the sizes of stars. There's Jupiter compared to Wolf 359. Wolf 359 is a very small star. You can see it's really not that much bigger than Jupiter. Then we have our Sun, which is more than 10 times the size of Jupiter, or 1,000 times the volume. And there we have Sirius, the bright star in Canis Major that we see in the winter. So clearly Sirius is very large compared to our Sun. Excuse me a second while I just take a drink of water. Okay, let's do that again. Let's take Sirius and put it in the bottom left. Now we have Sirius, next to that Pollux. Next to that we're getting to the giant stars now. There's Arcturus and then Aldebaran. So Aldebaran is absolutely huge compared to Sirius, which remember is already bigger than our Sun. But that's not the biggest star we know of. Let's take Aldebaran and put it in the bottom left of the next pane. Rigel is larger still, and Antares and Betelgeuse are supergiants that make Aldebaran look tiny. Again, that's not the biggest star we know. Betelgeuse is certainly very large, and the record for the largest star we know changes from year to year, but in this particular panel I'm showing Betelgeuse on the left, and then one of the largest stars we know about is VY Canis Majoris. I'm not sure that's the record holder anymore, but it was a little while ago when I put this presentation together. Understanding the difference between the Sun, for instance, and VY Canis Majoris, we've said the masses don't change that much, but clearly the sizes do, so there must be a huge difference in the density of these stars. And just to put it in some sort of perspective, let's have a look at the difference between our Sun and the last star in that sequence, VY Canis Majoris. And if you're having difficulty seeing the larger star, let me bring it in from the right hand side. Okay, now this is an exaggeration. I'm not exaggerating the size of VY Canis Majoris, I'm exaggerating the size of the Sun. Because if I didn't exaggerate the size of the Sun, it might be smaller than 1 pixel in my monitor or the projection system that you're looking at. So the differences in size are absolutely vast. So we can already tell that because we know the masses don't differ that much, VY Canis Majoris must be a very low density star to be that sort of volume. So we know that massive stars don't have very long lives, live fast, die young. But what happens when the fuel runs out? We call it nuclear fusion, or sometimes it's colloquially known as burning. In other words, burning hydrogen to make helium. This is nothing to do with burning in an oxygen atmosphere, like burning a piece of coal, but still nuclear fusion is sometimes called burning. Fusion of hydrogen to helium doesn't use up much of the star's mass. Remember the numbers that I was quoting earlier. 620 million tons of hydrogen is converted into 616 million tons of helium every second, and the remaining 4 million tons is converted into energy that's radiated out from the core. But notice that that's less than 1%. Even after 10 billion years, our Sun will still have approximately 99% of its original mass. Only a tiny fraction is actually converted into energy through E=mc². Basically, hydrogen is changed into helium, but most of the mass remains. And that's something that's a little difficult to get your head around, because you sort of assume that if a star burns for 10 billion years, surely the fuel gets used up. Well, it does get used up, but the mass doesn't get used up. The hydrogen is converted into helium. So what happens when the hydrogen runs out? Okay, remember the ABC of stellar evolution? This is sort of why I think ABC is a reasonably good way of just remembering what's actually going on inside a star, because we can use the ABC to figure out what's going to happen. When the hydrogen runs out, or at least starts to run out, the radiation will start to drop, and the star gets out of balance, because remember, balance is when gravity is equal to radiation, but if the radiation drops and gravity is still pulling and trying to compress the star, then the star gets out of balance. There's the B of the ABC. If it's out of balance because gravity wins over radiation, then the star will shrink and compress. And we know from the C of the ABC that compression heats the core. What happens when the core gets hot? Remember, positively charged particles, like originally hydrogen, but ultimately then helium nuclei as well, don't want to get close together because they're positively charged. But if compression produces heat, then the higher temperature can force the nuclei together and accelerate the fusion of helium into heavier elements like carbon, nitrogen, oxygen, etc. And when you accelerate the fusion process, the radiation levels come back up again, and the increased radiation puts the star back into balance. The original balance of the star is restored. So you can see this ABC in principle is a cycle, because there's nothing to stop this happening more than once. If the helium runs out, what's going to happen? Well, it'll get out of balance, which means gravity wins, which means compression, which means acceleration of the fusion process, and that will restore the balance again. So stars are beautiful self-regulating systems. For as long as the fuel exists, either in the form of hydrogen or helium or heavier elements, it'll self-regulate. I mean, in a sense, stars have to be self-regulating, because if they weren't, you wouldn't get stars lasting for millions or billions or trillions of years. They have to be self-regulating to make sure that this balance can be restored when any system gets out of balance. So with the ABC, we can understand how this process operates. That is a periodic table of the elements, which is a little bit frantic. Let's take the colours down a little bit and remind ourselves that in the top left-hand corner there's hydrogen, top right-hand corner there's helium, and when we fuse heavier and heavier elements, we work our way along the periodic table from helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, etc., etc., and this whole process can keep going all the way up to iron. Now, iron is special because we can fuse elements up to iron and the fusion process will release energy. But that doesn't happen beyond iron. I'm not going to talk about the nuclear physics of exactly why it's the iron nucleus that's the tipping point, if you like. But any elements above iron, if you want to fuse them together, they do not release energy. So how do you get silver or gold or lead, for instance, which are much heavier, of course, than the element iron? Well, we know that hydrogen fuses to make helium, and then we can go beyond that to carbon and neon and so on, silicon, etc., all the way up to iron. Nuclear physics tells us that the amount of energy released is dictated by this graph on the right-hand side that effectively tells us if we fuse elements up to iron, we get a release of energy. But then this curve turns over for reasons I'm not going to go into, which means that if we want to fuse elements above iron, it needs an input of energy. It doesn't release energy. It's not a mechanism that can allow a star to continue its life. So what energy can we possibly use that allows us to fuse the nuclei of iron atoms in order to make silver, gold, lead, etc.? Where do the heavy elements come from? Well, we can't simply allow fusion to take us all the way beyond iron. Fusion takes us up to iron, but no further. To go beyond iron, we have to look beyond normal star life and look at star death. For a medium mass star, by which I mean something not too dissimilar from our sun, gravity may not be strong enough to hold on to the outer layers when helium starts to be fused to make the heavier elements, carbon, etc., in the core. And so the star will expand simply because with not enough mass, gravity can't hold the outer layers in. The outer layers will expand, and because they're expanding, they will cool. Remember, compression produces heat. Expansion cools a gas. So as the star expands, it cools and reddens, and the star becomes a red giant. Let's remind ourselves where red giants are in this so-called Hertzsprung-Russell diagram of luminosity on the vertical scale and temperature on the horizontal scale. Remember, the sun was in the middle of the main sequence here. Red giants are colder, so their surface temperature might be only half the surface temperature of the sun, but they are a lot larger, so with a larger surface area, they are more luminous. Hence, they are higher than the sun in this diagram and further over to the right. The helium burning in the core can become rather unstable, and if the outer layers are given enough energy, they can be blown off the star completely. In other words, gravity is not enough to hang on to the outer atmosphere of the star. The molecules in the star, or the atoms or the nuclei in the star atmosphere, are given enough velocity to reach escape velocity, and the entire outer part of the star gets blown off to form a so-called planetary nebula. What's left behind when the outer part of the star has been blown away, the core of the original star, is what we now call a white dwarf. And a white dwarf is there. Remember, this is the core of the star after it's lost its outer atmosphere. And therefore, it's relatively small, but it's relatively hot, which is why the white dwarfs are down here. They are further along to the left, which is the hotter part of the Hertzsprung-Russell diagram. But because they're rather small, they have relatively low luminosity, despite being rather hotter than the sun. With an outer part of the star blown away, producing a nebula like this, you can perhaps understand why they were originally called planetary nebula. Some planetary nebula are quite spherical, and in a small telescope, if you can't quite see what it is you're looking at, you might mistake a small planetary nebula for a planet, which is why they obtained this name in the first place. But some planetary nebula are certainly not spherical. They have rather intricate shapes, and planetary nebula are being studied to try and understand the process by which the outer atmosphere is shrugged off the star, and what process can possibly produce structures like this. It's assumed that it's related to the rotation of the star, and possibly the fact that the star was a multiple star. Maybe this is the result of a binary star system and the material getting thrown out into space in a rather weird way because of the orbits of the stars involved. For high mass stars, well, the gravity is stronger, and so the star might stay together even beyond the point at which helium is burning to make carbon, nitrogen, oxygen. If the mass is high enough, the gravity is strong enough that the star holds together and doesn't become a red giant like our sun would do. At the end of its life, remember, this can keep happening all the way up to iron, but once you reach iron, in other words, hydrogen fusing to helium, and then helium fusing to carbon, and eventually to neon, silicon, etc. Once you reach iron, you can no longer fuse iron to keep that process going. And so ultimately, the core undergoes a catastrophic collapse. The collapse crushes the core to the size of perhaps only a few kilometers, and a shockwave rebounds from the core and is responsible for ejecting everything else above the core into interstellar space. What we end up with is a supernova. And the most familiar supernova remnant for most of us is the Crab Nebula, here imaged by the Hubble Space Telescope back in 2005, some 20 or so years ago. If we compare that with a more recent image from the James Webb Space Telescope taken just a couple of years ago, if I flick backwards and forwards between the two, if you keep your eye on some feature, perhaps this feature over here that my cursor is pointing to at the moment, if I flip backwards and forwards between Hubble and James Webb, these two images have been aligned very carefully on the stars, so the apparent jump in the nebula is a genuine increase in the size of the nebula over 20 years. This supernova went off about 1,000 years ago, and so 20 years is a couple of percent or so of the whole lifetime of this nebula, which is why in the James Webb image it seems to be a few percent bigger than in the Hubble Space Telescope image. So we don't tend to think of nebula changing, but in this particular case, over a period of many years, we can see a distinct change in the size of the nebula. There are other changes visible as well, because the James Webb is looking at the infrared, not the visible part of the spectrum, and so we are seeing different structures, but we can still see that change in size as the material is blasted away from the central star. The energy of a supernova is absolutely mind-bending. You can do a very quick back-of-the-envelope calculation and ask, well, how much energy does it take to rip a star apart? regardless of the mechanism that's going on inside, you can still say, if you start with a star that's in one place and you end up with a star that's splattered over interstellar medium, you can calculate how much energy, roughly speaking, would it take to do that. And you find that the answer is about 10 to the power 44 joules. Now, joules is not something we can easily get our head around in terms of anything that's that big, but the easiest way of imagining an energy of 10 to the 44 joules is think about the total energy output of the sun, not just the tiny amount that actually arrives on Earth and keeps us warm, but think about all the energy that's going in all directions in the solar system, and think about that energy in each and every second of the sun's 10 billion year lifetime. If you imagine all of that energy being released in just a few seconds, that gives you an idea of just how dramatic a supernova is. The word explosion isn't really appropriate, and really it isn't big enough to describe a supernova. The chaos that results and the energy that's released is responsible for fusing together elements heavier than iron. So remember, fusing iron doesn't release energy, but if you give it enough energy, you can fuse iron into heavier elements. The various elements generated during the star's life and its spectacular death are ejected into interstellar space. So a number of the heavy metals found on Earth were made in a supernova. So that means that the sun must be at least a second generation star, probably more likely third, fourth, fifth, sixth, seventh, eighth generation. There were many generations of stars, some of them very massive, that generated supernova and ejected the heavy elements into the interstellar medium, and that seeded the space around the cloud that ultimately became our sun, and that gave us heavy elements in the solar system and ultimately heavy elements in the Earth. So we owe our existence and these heavy elements to some unknown star that was born and lived and died billions of years before our sun was even born. After a supernova has crushed the core, what's left behind? All of the outer part of the star has been seeded back into interstellar medium. What's left behind is probably a tiny star, maybe only a few kilometers in diameter, a neutron star. It is thought that although supernova will generate a lot of heavy elements, it's thought that if you generate a number of neutron stars in supernova explosions, eventually some of these neutron stars will collide with each other, especially those that are made in binary systems, and the collisions of neutron stars are also thought to be an origin of heavy elements, because again the energy involved in two neutron stars colliding is enough to fuse iron into heavy elements. So neutron stars are very extreme bits of physics. We're talking about densities which are comparable to the nucleus of an atom. We're talking about a mass comparable to the mass of the sun, but being concentrated in a sphere that's only a few kilometers in diameter. The magnetic fields will be very strong, as indicated by this artist's impression, and by the conservation of angular momentum. When you take a large mass and compress it into a very small volume, any spin of the system gets faster and faster and faster, like an ice skater pulling their hands in to accelerate their spin. Now, the magnetic field of a neutron star might not be aligned with the spin axis. So what you can end up with is a sort of lighthouse effect, whereby as the star spins, the magnetic poles point in different directions, and charged particles can be accelerated by the magnetic fields and give rise to radio emissions, which are detected on Earth as pulses because of the rotation of the star. So by measuring the speed at which we pick up radio pulses from neutron stars, we get an idea of how fast these stars are spinning. So let's have a look at a few possibilities. A star that goes under the name, a pulsar that goes under the name of B0329, spins a little bit faster than 1 revolution per second, a period of 800 milliseconds. A much faster pulsar is the WvAS pulsar. Now we're talking about a period 10 times faster, a period 89 milliseconds, more than 10 revolutions per second. Remember, this is a star with the mass of the sun, rotating 10 times a second. Faster still, the Crab pulsar, 33 millisecond period, so fast you can hardly hear the individual pulses. You might want to put your fingers in your ears for the next one. 5 milliseconds, 200 times a second. Not the record holder. Here we go. Sounds like a mosquito. Period of 1.5 milliseconds. And it's difficult to think of anything, the mass of the sun, rotating close to 1,000 times a second. Very close to the point where it's pulling itself apart. Parts of the star will probably be moving at a fair fraction of the speed of light. And I've said here that that last pulsar had a period of 1.5 milliseconds. Not strictly true. Its actual period is 1.557806448872775 milliseconds. That is the accuracy, the precision with which we can measure these things, and the pulsar stability is so good we can actually use them to actually check our atomic clocks here on Earth. And we need to check against multiple atomic clocks to make sure that we know whether it's the clocks that are wrong or whether it's the pulsars that are changing their period. But they are very stable metronomes in space. That turns out to be very useful if, for instance, we're looking for the way gravitational waves throughout the universe change the timing of pulsars from various parts of our galaxy. We can actually use them to infer changes to the way space and time are distorted between us and those pulsars. The extreme, if gravity is so strong that it doesn't even make a neutron star, it is possible that the crush of the core during a supernova might produce a black hole. In other words, not a star a few kilometers in diameter, but once you crush it smaller than, for a star about the mass of our sun, once you've crushed it down to something smaller than 3 kilometers, then as far as we can tell, nothing can stop the gravitational collapse of the matter. We can't see black holes, but we can infer their existence. In this case, this is a supermassive black hole that's been imaged at the center of the galaxy M87, hence the designation M87 star. We can determine the mass of this black hole to be about 6.5 billion solar masses, and this image obtained by the Event Horizon Telescope, a collection of radio telescopes across the Earth, using the collection of telescopes as an interferometer to give us effectively a telescope with a diameter equal to the diameter of the Earth. We see the accretion disk. This is matter that's accumulating around the black hole, circulating around. Some parts appear to be hotter than others. This is partly a relativistic effect of the circulating matter around the black hole. Some of this matter is coming towards us, some of the matter is moving away from us. That makes some part of the accretion disk look hotter than other parts of the accretion disk. Light that's coming from the black hole can't reach us. There's a shadow region right in the middle. Because gravity is so strong, any light that's leaving that region finds it very difficult to arrive in that direction, and therefore we get this shadow in the middle. The black hole itself will be a little bit smaller than the dark region in the middle of this donut. Not only can we see an accretion disk around the black hole in this galaxy, we can also see one around the black hole in our own galaxy. This is Sagittarius A star, a somewhat smaller supermassive black hole, only 4 million solar masses. But because the centre of our galaxy is so much closer than the centre of M87, it appears a very similar size in the sky, which is why it was decided to try and image this at the same time they tried to image the M87 black hole. Again, we see a donut. Again, we see bright parts of the accretion disk. We think these are circulating around the black hole rather rapidly, which makes it rather difficult to image because they're moving so fast. And it is hoped that analysis of more data of this black hole should be able to reveal some of the dynamics of how materials are circulating around the black hole. Let me summarise by giving this graphical summary of what it is I've been talking about this evening. We're talking about starting with a cloud of hydrogen which might be enriched with some of the heavier elements if the cloud has been enriched by the evolution of previous stars going through their cycle of producing planetary nebula or supernova and seeding the material back into the galaxy. So we're starting with a cloud of mainly hydrogen and maybe a little bit of heavier stuff as well. The triggers that produce the cloud and make it collapse, well, a number of different triggers. One of the triggers might produce a small star, similar to our sun. Our small star would survive for many billions of years. Gravity would ultimately be in balance with radiation from burning the hydrogen to make helium. At the end of its life, perhaps 10 billion years later, the outer part of the star will swell up into a red giant. And if the helium burning in the core is unstable, it can produce a planetary nebula. In other words, gravity is not strong enough to hang on to the outer part of the red giant, and some of that outer atmosphere will be sloughed off and distributed back into interstellar space, producing a planetary nebula. What's left behind, you can just about make it out in the very centre of the planetary nebula. What's left behind is the core of the original star, and that is what we call a white dwarf. A white dwarf may be about the size of the Earth or so, 10,000 kilometres or thereabouts. There are no longer any nuclear reactions keeping this star warm, which means a white dwarf starts off white simply because it's hot, because it was the core of a star, but eventually the white dwarf will cool off and become a black dwarf. That same cloud on the left-hand side could possibly collapse, and as well as making small stars, it might make large stars as well. Stars with a mass, let's say, 10 times as massive as our sun. In which case, it won't last as long. It won't last for billions of years because the fusion process would have to be so fast to balance the very strong pull of gravity. At the end of its life, which might only be millions of years, it will swell up into a red supergiant, and if it's massive enough, when it gets to the point where it's trying to burn iron and can no longer support the enormous gravitational pull, because once you get to iron, you can no longer release energy, then that star might become supernova. Again, most of the material in the atmosphere of the star will be seeded back into the interstellar medium as the supernova redistributes all of those elements, including a lot of the heavier elements, including some made during the supernova process. What's left at the core might be a neutron star, only a few kilometers in diameter, but if the mass of the original star is high enough, then the collapse of the central core will not even stop at the level of a few kilometers. It'll be crushed effectively out of existence and produce a black hole where not even light can escape, though there might well be an accretion disk of matter around the black hole, which makes the black hole visible by its effect, not the black hole itself. So remember, regardless of whether we're making small stars or large stars, we'll either end up with a planetary nebula or a supernova, and both of those will recycle material back into the original interstellar medium. And so the interstellar medium with every cycle of every star becomes more and more enriched with the heavier elements. So the very earliest of stars would only have had hydrogen and helium in them, but stars that are a result of many generations of stars going through these cycles, more and more stars will be born with heavier elements, such as our Sun and, of course, the Earth, with of order 100 elements in the Earth's crust. So there are lots of details about stellar evolution that I have not gone into. But the point I'm trying to make this evening is we can understand the basics of how this cycle works and why it is that stars go through this evolution by thinking about acceleration of fusion, the balance of forces, and the fact that compression of the core produces heat. We can understand an awful lot if we just think about the ABC of stellar evolution. Thank you for listening.